Today, class, we continue 3.2. 3.2 will be electromagnetic induction. It will be more complicated, but very interesting. Okay, so if you learn because of exam, I think you might stress. But if you learn because you really want the knowledge to understand better, it will be amazing.
Magnet into the wire loop. You saw that as the magnet was moving into the wire loop, the needle bumped up positive. But now the needle isn't moving at all. This is a very important bit of Faraday's law. There's only a current when there's a change in the magnetic flux. It doesn't care how much magnetic flux there is through the coil. Right now there's a lot. All that magnetic field is through the loop. What matters is when it's changing. So now I'm going to pull the magnet out of the coil. And what you see is that while the magnet was leaving the coil of wire, the current was negative. So we get an opposite effect. And we'll talk a lot more about that. The effect is proportional to the number of windings in the loop of wire. So we should see a bigger effect through this loop and finally for the third loop. So we definitely saw a bigger current, went all the way to the maximum and minimum, and then I think we actually pegged out here. It went beyond the maximum this galvanometer will measure.
Here, you see, number one, we'll be using a galvanometer. So this is a zero. We call this as a zero-centered galvanometer. So this galvanometer pointer can deflect either to the left or to the right, depends on the direction of current. So if the galvanometer pointer deflect, so it means that current flowing. Okay, so this apparatus setup only consists of galvanometer and coil. So there is no battery, there is no power supply connected. Okay, so only coil connected direct to the galvanometer. Okay, so when the magnet is pushed in, you can see that the galvanometer pointer deflect to one side. Okay, let's say to the right. And then when you pull the magnet out, you will see the galvanometer pointer, okay, deflect to the other side. Okay, push in, it deflect to one side. And when the magnet stationary, the galvanometer pointer go back to zero. Then you pull out, it will deflect to one side and go back to zero. Okay, so just like this demo just now, you can see that when the magnet is stationary inside, okay, so the galvanometer does not show any reading. Okay, so it means that the galvanometer only deflect when there is a relative motion between the coil and the magnet. Okay, if let's say both stationary, there is no reading. Okay, so it means that there is no current. All right, so this is what we call as electromagnetic induction. Okay, process to produce induced EMF. Okay, when there is relative motion between magnet and also conductor. So this relative motion between magnet and conductor is actually what we call as the cutting of magnetic flux by the conductor. If you are able to see the magnetic field lines around this magnet, so when you move the magnet in, so this conductor actually cutting the magnetic field lines. What is amazing is once the magnetic field lines is cut, it will join back. Every time it cut, it will join again. And every time the magnetic field lines is cut, the electron in the conductor will move to one direction. What is the difference between magnetic field and magnetic flux? Magnetic flux is the same as magnetic field line. Let's say we have magnetic field. We can't see it by using our naked eyes. So we draw lines to represent the magnetic field. The magnetic field lines is actually the same as magnetic flux. Okay, yeah, sometimes I use the word magnetic flux, sometimes I use magnetic field lines. Magnetic field refer to the region around the magnet. We draw lines, okay, to represent the density of the magnetic field at that region. Okay, any more question? Is that clear? Clear, all right. Magnetic induction is the production of induced current, okay, or you can also write induced EMF. Okay, because when there is current, so there is EMF, but you can't see the electromotive force. EMF is electromotive force, okay? Just like this, when you move the conductor up, okay, the galvanometer pointer deflect, showing that current flowing in this conductor. All right, then the current that flow without any battery in the circuit, we call that as induced current. Induced means dipaksa. When you move the conductor downward, okay, it still deflect to one side, showing that current still flowing. Okay, so when current is detected by the galvanometer, so there must be electromotive force, but we can't see it. Okay, so that's why when we want to define electromagnetic induction, we can use the word the production of induced current or induced EMF when there is a relative motion between conductor and magnetic field. In some other book, they define it as production of induced EMF, induced current when there is rate of change of magnetic field by the conductor. Both is accepted. Okay, so how induced current is produced? Produced only when there is relative motion. Relative here refer to both of these. They are not moving in the same velocity. They are moving, if let's say both of conductor and magnet move in the same velocity, there will still be no current produced because they have no relative motion. Relative motion means they move in different velocity. They can move in the same direction, but one may be faster, one may be slower, or they can be moving in opposite direction. Okay, either one moving also can. Okay, all right. So if let's say you use a solenoid, okay, like this, a coil solenoid, connect to a galvanometer, and you move magnet in and out, also you will see the current. Okay, like this also the same, but must remember the magnetic field lines must be cut. Okay, magnetic field lines must be cut. Say here is north pole, here the magnet, and then this side is south pole. All right, so the magnetic field lines will be from north to south like that. So this normally we use magnetomagnetic field. If you can see it, it will be just like a cuboid. There will be a lot of magnetic field lines if you can see it. The stronger the magnetic, the magnetomagnet, the denser the magnetic field lines. If you are able to see the line, it will be amazing. All right, then this is the conductor. Okay, conductor. So if you move the conductor up, down, up and down, okay, it can cut the magnetic field lines. But if let's say you move this conductor like this, parallel to the direction of the magnetic field, it won't cut the magnetic field lines. All right, so the motion that you need to do will be following number 1 and number 2. Then only the galvanometer pointer deflect. But let's say you move parallel, okay, to the magnetic field lines by the real magnet, there will be no cutting of magnetic flux. So there will be no current. Okay? That one you must remember, must clear. So the magnetic field, let's say this is the motion, all right, and the magnetic field lines like that, then it will cut because this is 90 degree, right? Teacher, can I say cutting of magnetic field instead of magnetic flux cut? A correct term will be cut magnetic flux, because magnetic field refer to the region, around the magnet, the magnet. Can I use the word magnetic flux cut instead of cutting? Can Jason? That one no problem. Okay, we proceed. From time to time, I will read the chat box. Okay, so if you have question, then I can answer direct. Or if let's say you use the microphone, 1 or 2 person on microphone, it will be more fun. Last time in class, cikgu marah you all bising, right? Now cikgu nak you all bercakap. Last time in class, how I wish I can mute. Okay, if let's say you talk so much. Now I want you to talk some more. All right, so I'll continue. So we use right hand Fleming's rule to determine the direction of current. FBI, FBI, okay, FBI in US, Utara Selatan. Okay, that time is in Utara Selatan, means at north south. So you can remember that the magnet, the direction of the magnetic field is always from north to south. Okay. Okay, F, B, I. I is current. F is the force. So right hand also like that. You can label with the same method. F, B, I. Okay. So when we have magnetic field, and this magnetic field is cut by conductor, okay, by force, conductor move, right? So current is produced. So we open our hand like this lah, okay. When there is force, okay, conductor cut the magnetic field lines, induced current is produced. As for left hand motor, you want to produce force. Okay, to produce the force, first you must have magnetic field. Okay, and current must flow in the conductor. Then only the motor move, called catapult force. When you use your left and right hand Fleming's rule, so make sure all the fingers are perpendicular, okay, 90 degree. But let's say you have problem to make sure that all your 3 fingers are 90 degree, what you can do will be just do like that. Okay, and you imagine there is a pen coming out from your palm that represent current. So this is your thumb is the force. So this is the magnetic field from north to south. And then here will be your current. Okay, the easy maybe for you to move your hand. Okay, that is another method. But that is not the Fleming's left hand rule. Fleming's left and right hand rule still using like this. Okay. Look at this diagram. Okay, imagine the motion of this PQ, conductor PQ is downward. Okay, what will be the direction of the current in PQ? From Q to P, is it? P to Q. Okay, so you use your right hand Fleming's rule. So from north to south, so that will be your pointer. Okay, and then direction downward. Okay, jangan salah tangan. If you use your left hand, memang the direction will be wrong. So this one must be right hand rule. Okay, and then the direction will be from P to Q. Okay, right hand rule. So no problem. Okay, direction will be like that. Next, how to indicate the direction of the induced current in the solenoid? Okay, just now, when we want to determine the direction of current for a straight wire, okay, like this, we can use our right hand Fleming's rule. But if it is a solenoid, we can't use right hand rule for a solenoid. So we will use there are two methods actually. A simple method will be by using your right hand grip rule again. Okay, but that actually relate to Lenz law. Okay, so Lenz law state that the induced current is always in the direction that opposing the change in the magnetic flux that producing it. Induced current flows in the direction oppose the change in the magnetic flux that produce it. You see, the current is produced by the change of magnetic flux. And Lenz law said that the direction of that current, the induced current, will be always oppose the change that produce it. So remember, Lenz law, it relate to the direction of the induced current. Because in this subtopic, we have two law. One is Lenz law, the other one is Faraday. Lenz relate to direction of the induced current. Okay, so since now you know that the induced current produced when there is cut in the magnetic flux by the conductor, so there must be magnet, there must be conductor. Either one will be moving. There will be relative motion between magnet and solenoid. Okay, let's say both is moving towards each other, or maybe one is stationary, the other one is moving to another one. The polarity of the end of the solenoid that facing the magnet will be, it will try to, see here, oppose. So if let's say move, let's say north, moving towards the solenoid. So the end of the solenoid will try to oppose. It will have what? What pole? also north pole because it opposes. Don't want the magnet to go in. If let's say the magnet going out, so the polarity will be south because it want to pull back the magnet because it always opposes. Okay, I give you this example will be better. Okay, so now you see this is a galvanometer pointer, zero-centered galvanometer pointer. It can move to the left or to the right. Okay, so when this magnet is being pushed towards the solenoid, okay, north pole, move towards the solenoid. First, there is no deflection. So I mean that first is pointing to zero. When the magnet moving towards the solenoid, so there will be current produced. And the direction of the current produced here try to oppose the change that producing it, which is the north here. So here will become north pole. If here become north pole, here will be south pole. So still remember the right hand grip in chapter in the first subtopic. So use your right hand grip. So your thumb pointing to north. How to draw? And your four fingers will be like that. Correct or not? So your thumb now pointing to the north. Remember the first subtopic? So your four fingers follow direction of current. Current will be downward. So the current here will be downward like that. Okay, what is important is you look at the last wire. Okay, so coil wind like that. So here we go down, go here, and then the deflection will be to the right like that. So when magnet is pushed towards, okay, the magnet push towards the solenoid, so the end of the solenoid will become same pole as the magnet that is pushed in. Okay, so here is north, so here will become north. Then here will be south. Use your right hand grip rule from 3.1. Okay, so your thumb pointing to north, your four fingers follow direction of current in the solenoid. So the last one here is important. Follow how it winds. It will deflect to the left. So now, assume the magnet already inside. Okay, the magnet already inside this but stationary. So means that there is no deflection of the galvanometer pointer. Now, you pull the magnet out. Okay, what I mean is half of the magnet already inside lah, not to make you confused. Huh? So now you pull the magnet out. Okay, when you pull the magnet out, so there will be cutting of magnetic flux by this conductor. Alright, so when you pull the magnet out, there will be cutting of magnetic flux. So induced current produced in the conductor. And remember Lenz law, the direction of the induced current always opposed to the direction of the change that producing it. So here is north, so here become south. It will try to make sure the magnet still in. It don't want the magnet to go out. So here becomes south. Want to attract back this. Okay, so when here is south, here will be north. So again, you use your right hand rule, grip rule. Okay, grip right hand, north, your thumb pointing to north, and then your four fingers will be, how to draw? Your four fingers will be like this. Hopefully you can understand my drawing lah. Okay, so this is north, your thumb pointing to north, and then four fingers, grip, so direction up. So means that here, the current here will be up. If up, then you focus on the last one here. Okay, wind like that, right? So he'll be down like this. So like that. Deflect to the right. Direction of the induced current in the solenoid, you cannot memorize the diagram because once we change the way we wind the wire for the solenoid, then the answer might not be always the same. Okay, but if you can understand, then you can draw it, right? So just remember the concept. When you push in the magnet, here become same pole because they don't want the magnet to go in. When you pull out the magnet, here become opposite pole because they want the magnet to still be inside. Okay, then you mark which one is north-south, use your right-hand grip rule, label the current, and then slowly follow the flow of the current in the wire. Then you know which direction will the pointer deflect. Okay, so Faraday's law is related to the magnitude of the induced EMF or magnitude of the induced current. Okay, Lenz law relate to the direction of the induced current, but Faraday's relate to magnitude. If you still remember what is vector quantity is the quantity that have magnitude and direction, right? So the direction of the induced current, Lenz law. The magnitude of the induced EMF or induced current, okay, will be Faraday. Okay, so Faraday state that the magnitude of the induced EMF or induced current is directly proportional to the, here this is the keyword, rate of change of the magnetic field lines experienced by the conductor. Rate of conductor cuts the magnetic field lines. The more the magnetic field lines is cut in short period of time, the bigger the magnitude of induced current. When the relative motion is bigger, faster, then there will be more magnetic field line, there will be more induced EMF produced. For Faraday's law, can I say magnitude of induced EMF is directly proportional to the rate of change of magnetic flux? Yes, can. Correct. That is correct. What affect the rate of change of the magnetic flux? Number one is the relative motion just now, the speed of the relative motion. Number two, the strength of the magnet. Number three, the number of turns of the wire. The greater the speed, the greater the strength of the magnet, the more the number of turns of the coil, then the more the magnitude of the induced current or induced EMF. Okay, remember these three important factors that affect the rate of change of the magnetic flux. Okay, so the word in class that we use, rate of change of magnetic flux. We can also use rate of the cutting of the magnetic flux. We accept that. Okay, can be rate of change of magnetic flux, can be rate of cutting of magnetic flux. Same meaning. Okay. So can you guess for this diagram, which direction will the galvanometer pointer deflect? Alright, so we discuss. So magnet push in the direction, push in. So here north, so push in. They don't want to allow magnet go in, cannot go in. So must produce here same pole. Alright, so this is north. Use your right hand grip rule. Okay, your thumb. Okay, like that. Your four fingers like this, right? Betul kah? Yeah, so current going up like that. So here up. Here up. Okay. And then here wind behind, here up, then here will be to the left. Okay, good. Second diagram. Yeah, this diagram. Okay, logically will be right. Because why? If you want to be fast, you look at how they make the turns, all right? So it is opposite pole going in. Okay, it will deflect to the right. If you want the explanation, it will be here south going in, cannot. So here becomes south. Alright, so they don't allow the magnet to go in. Here becomes south, here would be north. Right, so use your right hand grip rule. So current going down. Current going down. Okay, going down. So here also current going down. So means that current flow from here. Okay, here going up. Okay, now deflect to the right. Okay, try this. To the right. Okay. Left. Which one? Gordon, are you referring to the correct diagram? This diagram. Okay, we discuss, you see. So now magnet actually inside, you pull the magnet out. Okay, so now it's north. So they don't want the magnet to go out. Okay, so they want to pull back the magnet. So they need to change here, become south pole. Okay, opposite pole, attract. They don't want the magnet to go out, so become south. So here will be north. Okay. So if let's say here south, here north, use your right hand grip rule again. So current going down. Okay, going down. So here will be up. It will deflect to the right. Okay, Ernie, okay? Okay, all right. Last one will be opposite. Okay, I proceed. Next slide. Application for this electromagnetic induction is actually in the generator. Okay, in the generator to produce current that you enjoy today. Okay, so this is actually a huge discovery, a huge discovery by Faraday. Faraday actually think of, if let's say current can produce motion, just like what you learn in 3.2, okay, current, magnet, produce catapult force, right? So he think the other way around. Can we have motion that produce current? So the generator is where the movement of conductor cut the magnetic field lines of the real magnet, produce current. And the current is being supplied to our house today by using another device, what we call it as transformer. All right, so we look at this video.
Do is attach a coil of wire to these giant turbines and place them inside a magnetic field. As the turbine rotates, the coil starts rotating and the wires start moving up and down inside the magnetic field. That produces the electric current. And this can now be used to light up things. These devices are called electric generators. They convert spinning or mechanical energy into electrical energy. So let's look at them in detail now. So let's start by figuring out in what direction a current gets induced or generated in this coil once it starts rotating. So let's say in our example, the coil rotates clockwise. Somewhat like this. Now, how do we figure out the direction of the induced current? Well, we have already learned something called the Fleming's right-hand generator rule, which says you stretch the fingers of your right hand like this, such that they are perpendicular to each other. Then the thumb represents the direction of the motion of the wire. That is the direction in which you're pushing the wire. The forefinger gives us the direction of the magnetic field. Then our middle finger will give us the direction of the current. So all we have to do is align our right hand to make sure the thumb and the forefinger point in the direction of the motion and the magnetic field. Then the middle finger will give us the direction of the current. So let's use our right hand rule on the pink wire that is going upwards, as you can see, and on the blue wire that is moving downwards. So it'll be a great idea if you can first see whether you can try it yourself. So go ahead and use your right hand and see if you can figure out the direction of the current in the pink and the blue wire. All right, if you've done it, let's first start with the pink wire. Because the pink wire is going up, the thumb should be pointing upwards. The magnetic field is to the right, so the forefinger should be pointing to the right. And so if we align our fingers that way, it will look like this. Since the middle finger is pointing inwards, this means the current in the pink wire must be inwards. Similarly, for the blue wire is moving downwards. So the thumb will be pointing down, the forefinger will still be pointing to the right. And so if we arrange our right hand over here, it will look like this. The middle finger is pointing out of the screen. That means the current in the blue wire will be coming out of the screen. So what we have seen is if a wire is moving upwards over here, then the current will be into the screen. And if the wire is moving downwards, then the current will be out of the screen. Remember this will be important. So now let's get rid of the hands and put arrow marks to indicate the current. And now we can guess what direction the current will be in the rest of the wires. Since the current has to flow from the pink to the blue, we can say that the current has to move here like this. And then the current has to move here this way. It goes out. It goes to that external circuit, maybe where there's a bulb. Look at that later. Then the current comes back like this and it flows in this way. And the current continues to flow like this as the coil keeps rotating. Because you can see the pink wire is still going up and the blue wire is still going down until we come to this point. Because now the pink wire starts moving downwards and now the blue wire starts moving upwards. See that? Again, if I go back and come back again, notice the pink wire is coming down and the blue wire is going up. This means now the current in the pink wire should be out of the screen, because we already saw using our right hand rule. When the wire is going down, the current must be out. And in the blue wire, which is going up, the current must now be inwards. In other words, the current will now change its direction. This is the important thing. So the current changes its direction and it continues to flow this way until again the pink wire comes on the left side. Because now again, the pink wire starts going up, blue wire starts going down, and as a result, the current in the pink wire will be inwards, the current in the blue wire will now be outwards, the current will again reverse. So every time our coil is in this position, which is perpendicular to the magnetic field, we will see that the current direction will flip. And so if you look at the entire animation now, it looks somewhat like this. Every time the coil comes in this position, perpendicular to the magnetic field, the current direction keeps changing. Now, of course, in the animation, I'm pausing the animation when my coil is perpendicular to the magnetic field so that we can see the current flipping its direction. But of course, in reality, the coil will be pushed continuously. There will be no stopping. There will be no jerking motion like we are seeing over here.
Okay, so far, can understand or not? So remember, when we are talking about generator, you must use your right hand rule. Okay, when we are talking about motor, then you use your left hand rule. Okay, generator must use right hand rule. Okay, and there must be cutting of the magnetic flux by the conductor. So this is just like the turbine, you know. Okay, so when it rotates, so there will be cutting of magnetic flux by the conductor. But in turbine, actually not the conductor that move, the one that rotate is the magnet. Conductor would be outside. Okay, but to make it simpler for you to understand, we look at this diagram first. Okay, let the magnet stationary, the coil rotating. Okay, and you can see that every half cycle, the direction of the current, this is what we call as induced current. The direction of the induced current in the coil, in the conductor, keep on changing. Okay, keep on changing. So the animation is showing alternating current generator since the current keeps switching the direction. Oh no. Okay, we just continue, then you will see later. Whether it is alternating current or direct current generator, the direction of the current here will be the same. Okay, the one that different will be the outer part later. Okay, keep on focusing.
Now, the next question we might have is, how do we connect this coil to an external circuit, like say to a bulb? Well, we could connect it directly, right? Well, let's see what happens if we connect the circuit directly. Current will flow, no problem. But as the coil starts rotating, notice the wires start twisting and tangling and turning and whatnot. That's going to be a problem. So to avoid that, we will not connect the wires directly. Instead, we will use an arrangement involving brushes and slip rings. It looks somewhat like this. So basically, we have two metallic rings, a pink one and a blue one. And what you may not make out from my diagram over here is that each ring is connected to one wire only. So the pink ring is only connected to the left wire. The blue ring is only connected to the right wire. And these wires are connected to carbon brushes, which is also conducting. And they are just touching these rings so that there is a metallic contact, but they're not stuck to it. So right now, there is a contact, the circuit is complete. And as a result, the current comes out of the blue ring, as you can see, moves this way, and current flows into the pink ring, goes like this. And when the coil starts rotating, as you can see, the rings rotate along with the coil. But since the brushes are not stuck to the rings just slip through the brushes. That's why they're called as slip rings. As a result, the brushes will not rotate. That solves the problem of wires twisting and tangling. And all the while, electric contact is maintained. Now, once our coil comes in this position, we've seen that the current reverses. So now, the current will flow out of the pink ring, goes like this, through the bulb, and now enters into the blue ring. So for every half a rotation, the current through the bulb also reverses. Let's say when the current is flowing this way, the bulb glows blue. And let's say when the current reverses and flows like this, the bulb will glow yellow. So now if you look at the entire animation, it looks somewhat like this. And so we have successfully built our generator. And what's interesting to see is that the current from that generator is continuously changing its direction. Such a current is called alternating current, or AC. And this might sound a little weird, but it turns out that when you want to transmit electricity over a long distance, like from the power station to your houses, then alternating currents, or AC, have some great advantages over unidirectional currents, or DC. And it's for that reason the current that we get at our houses, the electricity that we get at our houses, are all AC. And these generators are called AC generators. Finally, what if we want to build a DC generator where we don't want the current direction to change? We want it to remain the same throughout. Let's say in this direction. How do we do that? Well,
Okay, now can understand, huh? So we call this as slip ring. In BM, it is gelang gelincir. Okay, gelang gelincir. So it means that the slip ring, and then the coil here. Okay, so this right, the left side, okay, is shorter end. Okay, shorter end. It will be connected to the pink ring all the time. Means that it will rotate inside here, and it will be connected because it is the end of this short end is connected to the pink ring. So means that rotate inside the pink ring and all the time will be connected to the pink ring. Okay, and then the other end, okay, this one, okay, it go through the first ring, which is the pink ring, but not connected. It just go through it, but connected to the blue ring. So means that all the time when the coil rotate, so the short end all the time connect to the pink ring, and the long end go through the first ring and connected to the blue ring. Okay, so we call this as slip ring. Remember that, slip ring. Will AC generator be tested in exam? Yes, this is a famous SPM paper. They love to ask you, maybe they give you a DC generator, ask you to modify, do some modification so that it can become an AC generator. If you want to change it to alternating current, must use slip rings. Next, we will look at DC current. Okay.
to build that, first let's get rid of this ring. Alright, now to make sure that the current direction remains the same, what we will need is that these brushes to continuously keep changing contacts between these wires for every half a rotation. Let's see why. So if I want the current to flow this way, right now in this position, I can connect this brush to this wire, so the pink side, so that the current flows like this and comes out. But as the coil rotates, notice once it comes to this position, you've seen that the current starts flipping, current reverses. And so now, to maintain the current in the same direction, we would now require this brush to come in contact with this wire. That is the blue side, right? And Then again, once you come to this position, again it flips, the current flips, and again we would want now this brush to come in contact with this side. And so as a result, can you see that for every half a rotation, we would want the contacts to keep changing. But how do we make sure that happens automatically? We can do that by attaching split rings. Split rings, as the name suggests, is a ring that is split in between, giving two half rings with some gap in between. Now let's see how this arrangement automatically changes contact for every half a rotation. So right now, this brush is in contact with the pink side. But as the coil rotates and comes to this position, the current reverses. And now notice the brush is in contact with the blue side, making sure the current still flows in the same direction through the bulb. Again, as the coil comes to now this position, finishing another half a rotation, again notice it has changed contact. It is now in contact with the pink ring, connected to the pink side. This way, we have now built our DC generator, where the current only flows in one direction through any external circuit. And this arrangement, which helps us automatically change contacts, we call them as commutators. So split rings act like commutators. So to summarize what we learned, if you take a coil and spin in a magnetic field, due to electromagnetic induction, a current gets generated in that coil. Now the direction of the current depends on whether the wire is going up or whether it's going down. As a result, for every half a rotation, we see that the direction of the current keeps changing. And so this generator is called an AC generator because it generates an alternating current, a current whose direction keeps continuously changing. On the other hand, if we use split rings, then it acts like a commutator. It keeps changing the contacts for every half a rotation and makes sure that the current does not change direction in the external circuit. We call this a DC generator. And so this is how we can generate electricity just by rotating a coil in between a couple of magnets.
Okay, any question? So remember, let's say we want to create an alternating current generator. So we need to use slip ring, SLIP, slip ring. Okay, and then if let's say you want to produce direct current, okay, direct current generator, we change that slip ring to a split ring, SPLIT, split ring. Okay, another name for split ring is commutator. And when we say
is in contact with the pink side.
When we say direct current, so it actually here refer to the outside the external circuit. So the current in the external circuit here will be always in one direction. Okay, will be like this lah. For this is in clockwise direction. Okay, like that. All the time is like that. But for the alternating current just now, the outside nah, outside here, okay, it will be clockwise, anti-clockwise alternately. Like this is clockwise, then after that anti-clockwise, clockwise, anti-clockwise alternate. Okay, open to question. Any question? Popular question for this will be number one, suggest ways to increase the induced current or induced EMF produced. Number two, how to modify that generator to become, let's say from alternating current to become direct current. If let's say you want to suggest on how to increase the induced EMF or induced current produced, you can focus on what law? Faraday or Lenz law? Faraday, right? Okay, so means that you focus on to increase the rate of cut of the magnetic field lines or increase the cutting of the magnetic flux. So it will refer to the increase what? Increase the speed, relative motion. Next, what is it? Oh, Hubert?
Increase strength of magnet.
Increase the strength of the magnet. Okay, some more can use more number of magnet. More number of magnet also increase the strength of the magnet. Okay, some more
More number of turns of coil.
correct. Increase the number of turns of coil. Okay, so this part when you answer, normally this will come out in your paper 2 lah. Okay, direct current generator. So we have magnet and then we have wire here. This is actually coil, all right, coil. Then this need to be turned. Okay, so this need to be turned. Then current, there will be cutting of magnetic flux. So current will flow here and then go to the external circuit. Okay. So this one is the commutator. Okay, commutator reverses the connection of coil with the external circuit every half cycle. So that current outside always flow in the same direction. Okay, so in the real generator, just like whether you are talking about wind turbine, wind turbine, the turbine turn. So that turning is actually the force lah. Okay, force your thumb if you use your right hand rule, and then it cut the magnetic field lines. Okay, current produced inside. Okay, same goes to, let's say, nuclear energy that produce electric energy. Okay, so the nuclear in energy produce heat, so that heat will change water to steam, so the steam will rotate the turbine. Okay, turbine rotate, cut the magnetic field lines. The process continue. All right. Biomass and all the other source of energy, the M is actually to produce electrical energy, because most of our electric house use a lot of electrical appliances. Okay, so we need electrical energy. Okay, so that electrical energy is generated by using generator. Okay, so whether you are talking about wind energy or wave energy or hydroelectric, okay, so all actually they have something that is moving that cut the magnetic field lines. Okay, clear? Right. Okay, so you see, whenever the position of this, so we call this as armature, the coil. Whenever the position of the coil or the armature is like this, so the cutting of the magnetic flux will be maximum. And whenever the position of the armature is vertical like this, okay, so the cutting of the magnetic flux is 0. So here, there is no current produced. Okay, but since they have inertia, it keep on rotating, and you will see the galvanometer pointer deflect. Okay, so this actually is the current, is the direct current. Okay, one side. Okay, positive side. So you see why like this? So this actually refer to the magnitude of the induced current increases until maximum, then decreases until 0. Increases maximum, then decreases 0. Do you realize that 0, 0, 0 here is where the position of the armature is vertical? Okay, vertical 0. And then here also, no cutting of magnetic flux by the conductor. So 0 induced current, 0 EMF. But once it start rotate, okay, rotate until parallel, like this position, okay, horizontal, then you see a lot of magnetic flux is cut at this position. So slowly increases, right? The maximum. The process continue. Okay, so this is a direct current produced by DC generator. If you use this type of direct current, okay, your TV will be, your radio will have sound maximum, then slowly decreases 0, and then increase again the sound, and then reduce again. So in next topic, we will learn on how to make sure that the DC current, okay, is just like the one that produced by the battery, like this. We will do something to this, to the circuit, so that finally it become like that, not like that anymore. Okay. So this is for the alternating current, okay, alternating generator. Okay, so they are using what do you call this? Slip ring. Okay, see this end is shorter and then this end is longer. Go through the first coil and then go to the second coil. When it rotates, so it carry the end together. So it means that the short end will rotating inside the first ring, the long end, okay, will touching the second ring. Okay, the other will be the same. Okay, so you see, so here is 0 induced current. This the vertical axis can be induced current. You can also name it as induced EMF, electromotive force. All right, so see 0 here, also 0 here, also 0. So 0 means no induced EMF, no induced current. Means that there is no cutting of the magnetic flux. That is when the position of the coil or armature is vertical. See, vertical, like this, vertical. And then here also vertical. And then here also vertical. Okay. Then when the armature when the coil start rotating, can see that the magnitude increases here, rotate. So the magnitude of the cutting of the magnetic flux increases, hence the magnitude of the induced EMF or induced current also increases until maximum. Okay, that is the position horizontal. Coil is horizontal, maximum cutting of magnetic flux. Then it reduce again, okay, like that. Okay, then you see how here. So this is actually when you look at the deflection. So this is 0, and then here the deflection to the right. Okay, to the right. Then here 0 again. Then go down. Down here means that the deflection is to the left. Okay, so that is why for the alternating current, can see, so we use the positive side, okay, and then the negative side. The negative side doesn't mean that this is a smaller current. So here means the current increases, but in opposite direction. How split ring commutator ensure current flow in one direction? Okay, I show you again the video. First, the coil must be rotating. So let's say the motion of the coil is in clockwise direction like this. So the one that on the left side will always be upside, moving up. And then the one that on the right side will always moving downward. Then it can turn. If let's say both is moving to one direction, it will go up or go down together. Okay, so here, this one go up, here go down. Okay, so from your right hand Fleming's rule, if the direction of the movement, the force is up, okay, so north, south, so current will be moving in. This is the direction of the current. And then vice versa for this. Now, so see, so this end is always connected to this end. Means that when it rotates, it will bring this together with it. This split ring together with it. Okay. See?
Contact for every half a rotation.
It will
right
bring
now,
it together.
This brush is in contact with the pink side. But as the coil rotates and comes to this position,
can see?
The current reverses. And now notice the brush is in contact with the blue side, making sure the current still flows in the same direction through the coil. Again, as the coil comes to now this position, finishing another half a rotation, again notice it just changed contact. It is now in contact with the pink ring, connected to the pink side. This way, we have now built our DC generator, where the current only flows in one direction through any external circuit. And this arrangement, which helps us automatically change contacts, we call them as commutators. So split rings act like commutators.
Good lah. If you have question, you better ask. Don't keep to yourself. Otherwise, I also cannot. If let's say you don't ask, I don't know what is your problem. If you stayed until this part of the video, please comment down below 3 red heart emoji like this. Thank you so much. Till we meet again, insyaAllah. Assalamualaikum warahmatullahi wabarakatuh.